Okay, one thing I wanted to point out from last last lecture, we were looking at this equation. The reason for looking at it at the time was we wanted to find out about the velocity in the x direction. We were going to solve for that, but we really wanted to find out what was the, because of the magnetic field, what was the effective change in the Lorentz factor. We wanted to go from gamma to gamma star, and we did that. But I thought there was something else in this equation, or from this equation to this equation. This is a vector equation, and it said that the change in momentum per unit time was, the Lorentz force. And fortunately for us, the momentum, vector momentum, was just gamma mv. Gamma is a constant in the magnetic field. M is the rest mass, so that's a constant. So this equation, and no electric field applied, so this became the equivalent of F equals ma. And we said, well, we want to solve for the x direction of velocity, the acceleration in the x direction. So we took this, on this vector quantity, we said, well, v is approximately, it's in the z direction, and it's approximately c. That's what's driving all these oscillations. So we put in a scalar form, we took this and we approximated Vz by c. Okay, so so that gave us the oscillation in the x direction depended on the velocity in z, which was almost c, and by. And what I wanted to point out was that later, when we solved for the acceleration in the x direction, and we went, in fact, maybe it's just in the next slide. So yes, we solved for the velocity in the x direction. But then we went here and we said, well, listen, the velocity squared is vz squared plus vx squared. So having solved for vx, we could solve for vz. And this is what we got. Oh yeah, and there was, oh damn. There was a mistake in the slides, which I corrected before, but I see it's popped back. This 2 is not supposed to be here. This was a mistake. That's what threw me last time. And I had it corrected and uploaded, but now I see it's not corrected anymore. It's just a mistake here. Every place else is okay. But what I wanted to say was, so we solved the velocity in the z direction, and we got that it was slowed down a little bit. That's how we introduced the effective value of gamma. But we saw that there was also a double frequency. And where did we do? Okay, we saw that there was a double velocity, a double frequency velocity in the z direction. So if I went back here, that meant that there was a slowing down in this direction, but there was also a new Vz that we might not have been expecting. It was a sort of a double frequency here. So for every cycle of the magnet period, there'd be one cycle of V sub x, but there'd be a double frequency, 2 cycles, Vz. So that might bring us back to this. Also, before we were saying that this was a velocity in the z direction cross b, and we just took it as c. But now we see that there's an extra term, so maybe we could think about this as a perturbation thing here. We're representing this vector velocity by its components. So we started with the main, I could write this as v equals v0, which would be c, in the z direction. And then I could say, plus it has a component Vx at some frequency, we'll call it omega. And that's this that we found. And with the V0, so we got some oscillation, but then we find there was also a 2 omega popped up. And so now we have a 2 omega in the z direction crossed with the b in the y direction. So that component, this Vz, the 2 omega component, is going to give us another Vx direction. This is going to be z and y. It's going to give us another x. So the double frequency in z is producing another oscillation in x. And you can see this is just going to go on forever. It's a perturbation analysis, and lots of alternately orthogonal components are going to come. So again, the first one is just c. C in the Z direction, and then we get a Vx, and we'll get, I'm sorry, then we got Vx gave us with a Y, and now we have a Vz at double frequency crossing with B, and that's going to give us a third harmonic, okay? Always a little bit lower in amplitude. And now we have a third harmonic in the X direction, again crossing with B, and it's going to give us a fourth harmonic. And they're just going to alternate back and forth here. So I think that's a pretty clear concept, but somebody wave or say something.
Professor, when you said that the momentum is gamma mv,
Yeah,
you said that m is the rest mass. How
yeah,
important is that rest
yeah.
clarification?
The natural, this is, if you looked up in a table, what is the mass of an electron? They give you the rest mass. They might put a subscript E on it or some subscript, but it's not necessary to put a subscript on it. This is the rest mass, and gamma times m is the effective mass because of the motion. So this is the one that, this gamma m is what's increasing, okay? But this m is just the rest mass, and it is a constant. Okay, thank you. What do I want? So okay, anyway, so we talked about where the harmonics came from, but here mathematically I thought, well, you can see it by just doing a perturbation analysis with V having the various components, and by the vector nature of the equation, you see that they just alternate between two polarizations, okay? Two vector components. So I wanted to bring that up. And then we went through all of these things, okay? Oh yeah, and we calculated, so we got the undulator equation, so we know all the wavelengths that we're going to see on axis, off axis, and how it depends on the magnetic field K through this non-dimensional factor, which is of order K equals 1 for undulators. Could be a little bit less, could be a little bit more. As you go above K equals 1, those harmonics start to become more important. And at a certain point, that perturbation analysis doesn't work because the velocity, the harmonic components get to be pretty strong. And we defined a central radiation cone in combination with a bandwidth. We said that we're only interested in a 1/n bandwidth here, and let's define what angle contains the 1/n bandwidth. And we got this, the central radiation cone. And this is a good time to talk about it because in the slides that you'll see about the facility upgrades and going from an ellipse to a near circle, etc., there was a lot of calculations 2 years ago when we were presenting this in class and doing our own calculations, and the ALS had announced that it was going to do, it was asking the DOE for an upgrade for, I forget how much money, but it was way over $100 million, as I remember. And it was a significant thing in the literature. And I mentioned the ALS was telling the DOE that they were going to get an increase in coherent flux and coherent power. At the time, they said by more than 100. I think they said 200 or something like that. But at any rate, we were doing this in class at the same time. There was a workshop at LBL run by the ALS, which had the world's experts on how to calculate these things. And the calculations looked a little different to people because this combination, it was presented differently by some people. Some people chose a slightly different theta central. In fact, the most common one was to put a 2 in front here, so a smaller angle. But in the end, this is the power in a certain solid angle. So if you make the solid angle smaller by, if you make the angle smaller by 2, the solid angle by 4, well, for sure this power goes down by 4. But their bandwidth would be different because they were choosing a smaller angle. And when you get done, all the numbers came out more or less the same, within some small factor, less than a factor of 2. So if you see a lot of slides in there about different definitions of what the central radiation cone is, I think with what I just said, you can forget about it. You can just say, okay, we were told about that. But in the end, it takes you nowhere. One thing here, though, we calculated the power in the central radiation cone, and the bar meant that it was an average over a cycle or over an undulator of n cycles. And this is what we found. Again, the K is a measure of the magnetic field, but the reason it shows up here, and this comes up in one of the homeworks, the acceleration depends on K, we found. That was that calculation we were just looking at a moment ago. We calculated velocity in the x direction, but the time derivative of, so the acceleration was also there. And it depends on K, and power radiated depends on the modulus of the acceleration squared, so you get a K squared, okay? This part was because as you increase K, the electrons get slowed down, the gamma star becomes more effective, and the acceleration gets reduced. So this K squared for acceleration starts to get reduced, and the higher K gets, the more important the factor is. And so that's what these two things were for, okay? Small, really small K, less than, let's say, a half or less, this doesn't show up, and you just get the simple K squared for acceleration squared, the slowing down. What we added artificially, we just said, okay, this is what we calculated within our capabilities of our simple model. For people, in particular Kwang Jae Kim, who's now at Argonne at the University of Chicago, he has shown in papers over many years now that there's another term you have to take account, where you take account of power flow between harmonics, and he called it JJ squared, and JJ is some Bessel functions. And in fact, it reminds me, I told you there's an errata for the book. It's in this area of the book where the errata really starts to make a difference, because the JJ is mentioned there, but it's mentioned only in the sense of the fundamental. And we're about to talk about harmonics, and we needed a more sophisticated, a more complete definition of JJ, not just for the first harmonic, the fundamental. And so that's it's not in the book. These are developments beyond the book. And so in the errata, you'll get some of that. And there's also a mistake in the book. I forget what it is, but something in the undulator equation, I think we left out the plus sign or something like that. Anyway, there's a few things in the errata you need to get. But this term, we're going to look at in a moment, how this is defined. And again, it's in the book, but only for the simple case of n equals 1, the fundamental. When you're looking at n equals 3 or 5 or any of the others, you need a more complete definition, and that's what's in the errata. And okay, so this is just to repeat what those three terms are, okay? And so, yeah, so we basically took the existing formulations in the literature. We had all of this, and we argued that for the fundamental, which we were interested in at that time, this JJ squared term was like 15% correction or something like that for n equals 1, and we just stuck it on, okay? But now we want to take more attention to this. This we talked about. I don't think we need to talk about it anymore. Oops. This is more in the book than it is here, but generally by analyzing these various harmonics that show up and with what amplitude, we generally find that the power in the central cone for different harmonics scales as n cubed k to the 2n. So for n equals 1, this didn't show up, and this was just k squared. Well, what we found, this was for small k. But now we're going to use this, and that's what's coming up in the coming slides, that we're going to use our knowledge of this and just how it shows up in those JJ squared terms. And we talked about this. Okay, so here we get down to work. This is the formula that we had before, but it's now taking cognizance of the fact that we could use this formula for different harmonics if we just use this JJ squared term as it appears in the literature. When we wrote this formula, we didn't have an n here, but it was just because we were talking about n equals 1, so it didn't matter. But there's a little sentence here about why it's n, okay? So, and then this formula, so this is the formula that we've had before, except it has the JJ squared term, and this is a practical version of it. So if you had to do a homework calculation to calculate the power in the central cone for some number of harmonics, you could just use this formula here, okay? And now here is the JJ squared. Here's how it's defined, okay? It's Bessel functions, difference of Bessel functions, where this n is the harmonic number that you're looking at, and this the argument for the Bessel functions is this thing, okay? So it's a little bit messy, and that's why I wanted to leave this, basically leave it out of your hair. But now I find that actually it would be interesting to know what's the power, not just in the fundamental, but what about the third harmonic? We could use this actually, and we're going to, in the next slide, we'll show that we can do an expansion of this for small values of k, okay? For instance, k equals a half. This term, again, will be not so big, and you'll see in a moment how that goes. And by the way, so this is the formula, expansion of what we did before, now to include harmonics, okay? And it will occur in a smaller solid angle and in a narrower bandwidth, okay? Oh yeah, what about this narrower bandwidth? Was this clear to everybody about if you have an electron going through an undulator and it does n oscillations, we've said that, well, it produces a wave train of n oscillations. We think that if we do a Fourier transform of that, we'll find that the spectral width of that, if we were to put it through a monochromator, we'll have a spectral width of 1 over n. And it just has to do with how well you define a wavelength when you only have 10 cycles or 100 cycles or 1,000 cycles, okay? So what about the third harmonic? So you have electrons going through and they're doing, in one direction, they're producing a wave train of a certain polarization given by the x direction. And we see it has a bandwidth of, again, let's say 1 over n. What about the third harmonic? What the third harmonic means is every time the electron goes through one period of the magnet structure, it produces one cycle of radiation at the fundamental, but it's the third harmonic, it's producing 3 cycles. So one period of the magnet structure produces 3 cycles in this, in the third harmonic. So you could say that, okay, should I use my drawing tool? I'm sorry, but this thing writes, or at least I write with it so poorly. Let me see what happens. Where do I want to do this? Oh, yeah. That's a z-axis. So for n equals 1, let's say it goes through so many cycles, okay? But what about n equals 3? Whoops. In this one cycle here, the n equals 3 is going to go through 3 cycles. 1, 2, 3. And then in this next period of the magnet structure, the Vx, that's what this was, Vx of, let me call it omega, and this is going to be Vx of 3 omega. Okay, so this is the third harmonic, and again, it's going to go 1, 2, 3 cycles, and it's going to continue like that. And so when you look at this and you do your Fourier analysis through here, where this is time, you're going to find out that here, there was a central wavelength and a width that was 1 over n. But here, when you do a Fourier analysis of this thing, you're going to find that the central wavelength, if I do it in photon energies, rather than be here, it's going to be out here, and it's going to be narrower. It's going to have a width of, rather than 1 over n, rather than 1 over n, it's going to have a width of 1 over 3n. So it's just a Fourier analysis, okay? Okay. If you can, I guess I could do a, so I hope that was really enlightening. This formula then is, again, the power in the central cone for different harmonics. And this is in practical units, which says that, gamma is non-dimensional, but the current, if it's 400 milliamps, what this says by these brackets means what is the average current in milliamps? You just put 400 here. An ampere is 0.4, okay? JJ squared, you have to figure it out. Lambda U is the period in centimeters, so if it had a 3 centimeter period, you just replace all of this by the number 3. The units are already taken care of here for you, okay? And this is in units of watts, okay, power. But if you wanted it in photon flux, which is what the synchrotron people often present, this is just a conversion from power to photon energy, and that's all that is, okay? So did we get the Bessel function? Yeah, so here's the Bessel function. Here's the JJ squared term. It's the difference between the two Bessel functions squared. And for small k, which would be small x, this is what J1 looks like, and this is what J2 looks like. And if you go back, and x was defined here, okay? If you go back and you put those in, what you'll find is your original formula that we had is here, but the JJ squared term is replaced by this. This is what's left. This is what we had before. That's this part of the equation. It's everything but the JJ squared. And then there's the JJ squared term. So you just go through this expansion and you put it in. And if you combine these two terms, you see that, I just show it in the practical units case, the radiated power this is for the third harmonic. This example is for n equals 3, okay? You see that the power goes as n cubed k to the 2n. So for n equals 3, it's k to the 6th, k squared plus k to the 4th, and there's an n cubed. So this is giving you power in the harmonics. So I think one of the homework, I can't remember if the homework problems only look at the fundamental or they also look at the coherent flux or coherent power. But so there are two things going on here. One, we're extending our formulas to take care of harmonics, and the other, we're going to extend our formula to just take the coherent part, like we put a pinhole in front of the undulator. So, okay. I need some feedback. Angel, how does that fit?
That makes sense, sir.
Okay, Bailey, are you okay with this? So there's going to be two parts. We're going to take our formula and correct it as we did here, or add the capability to analyze harmonics. And then we're going to, in a moment, we're going to do the spatial frequency. We know a relationship for spatial coherence, and what would happen if we put a pinhole in front of it, and the formulas are going to change again, and they're going to get more complicated. And I was thinking I should avoid telling you about all that, but in thinking about this lecture, I decided it's really the hottest topic in the community. We shouldn't leave it out. So, yeah.
To confirm, so far we've taken care of harmonics, but not coherence.
Yeah, exactly. So here we took care of the harmonics, but we're talking about power in the central radiation cone. And in a moment, we're going to, or sometime today, we're going to get to power. We're going to replace this by coherent, COH, meaning it's not only in the central radiation cone, but it's actually spatially coherent only. It's had the equivalent of a pinhole put in front of it. These are curves.
So
Yeah.
I have a question on the K being much smaller than 1. What are the what's the order of magnitude that we're talking about with respect to K?
Yeah, good question. Yeah, so actually, maybe this is remember we had a power curve for different versus photon energy, and I told you that the peak of this curve actually occurs for K equals the square root of 2. It's one of the homework problems. And this thing, this is like K equals a half down here. And K equals 0 was a crossing. At K equals 0, there's essentially the magnetic field is not even felt, and there's no acceleration, and there's no power. So this is K equals 0 down here, and it's coming up to about K equals a half. Maybe 1 is up here, square root of 2 is here, and then you come down, okay? And these are curves, power in a central radiation cone. This, and we'll see old coherent power curves for the facilities as they exist now. There's a little asterisk here, which basically implies these are with the old parameters of the beam size, sigma and sigma prime. But all of these facilities and all the next facilities are all undergoing upgrades. In fact, ESRF has already completed its upgrade. APS is into it, and Spring 8 is still in the planning stages. This is just a comment I was telling you about. Sometimes people put a half in here. Actually, they even try other things. What they're trying to do actually by doing that is they want the depth of field of radiation to sort of match the undulator length. They're trying to do two things at once, and it has some advantage, but it doesn't really help in some ways. So anyway, we'll just use our definition where this angle contains a 1/n bandwidth. It's the simplest one that there is, and it works just fine. Beam parameters we talked about, right? So that there's a cross section, which for most facilities now is highly elliptical. In fact, for the ALS, I looked up the number, but it's almost 50 to 1, I think. In fact, right. If you were to take a look at your book, on page 154, there's a table that shows properties of the ALS and the APS. And if you go down there, more than halfway down, it has the sigma values. And for the ALS, the present sigma values horizontally is 251, and vertically it's 8.3. And their goal for the new upgrade is to make it 10 in both directions. So they're going to go from 250. We can guess, in fact, you're asked in the homework, what kind of increase in coherent power do we think we're going to get? Well, if you take an ellipse that's 250 and you bring it down to 10, first guess is we're going to gain a factor of 25, okay? There'll be some other factors I'll tell you about in a moment. But anyway, this is what a cross-section is imagined to look like, and with Gaussian distributions, but only showing it shaded through the RMS values, okay? So these are the Gaussians, and this is RMS in X and Y, okay? And in general, again, this is going to be highly elliptical. And also, this is divergence. The electrons, what is the angle that the electrons are making with the axis of the undulator? And basically, the electrons are not all parallel. They're slightly divergent. And if you want to have good undulator properties, you want this divergence part to be much less than the central radiation cone. The ALS does this quite fine because our central radiation cone is like 30 microradians. The APS and the hard X-ray facilities, they don't quite make this because their central radiation cone, 1/gamma square root of n, 1/gamma is so much bigger. Their central radiation is smaller, the divergence of the electrons in the bunch still about the same. So rather than get one of these nice sharp curves like the ALS has, they'll be more in sort of this region. They'll have a loss of a broadening of the spectrum because many of the electrons are going through not so close to the axis, close enough, far enough off axis that it takes them a longer time to do the N oscillations or the 100 oscillations. And because they're off axis, just geometry, their path length is longer, they're going to produce a lower frequency of radiation. That's what's happening here, lower photon energy, and they're going to have a broader spectrum. Oh yeah, and I want to tell you about these. I started to mention it before, but for instance, when we look at the beam size, we didn't do it here. Well, sometimes for both beam size and divergence, we'll say that, for instance here, we'll say that there's a total angle. There's a combination of the central radiation cone, but also the divergence of the different electrons is spreading that cone out. We calculated a central radiation cone, assuming that the electron was going right down the z-axis. If it's off by a little bit, okay, then it's going to increase the size of the central radiation cone. If we're in this condition where it's a relatively small parameter, it doesn't have a big effect. And in fact, many cases we can ignore it. There's a similar form, so we call that the total half angle. Central radiation was the half angle for the perfect case. Putting in some finite divergence of the electrons, we get a total angle. And this is going to come up in a moment. I'm going to tell you to ignore it in the end, but it's going to come up. And also, so this was because of the divergence of the electrons, but there's also one here. We'll say that there is a beam size. We'll see a formula there also that gets affected. We'll say that in general, the beam size just depends not on the central radiation cone, but on the sigma values. But we'll see there's a little correction to that also. And I put all of this in these lectures because we were intensely matching what the professionals were doing at all the different synchrotron facilities. And if they were including these little factors, we wanted to include the little factors also. I told you about brightness, I think, power per unit area per unit solid angle, and spectral brightness, where you ask not only how much of the brightness is within a certain bandwidth, 1 over n, 1 part in 1,000 or something like that, and that we call the spectral brightness. Okay. And all of the facilities use this as a measure of how good their facility is. In fact, when the ALS advertises that their coherent flux is going up, they're also going to show you that their spectral brightness is also going up by almost a factor of 100. Okay, and oh yeah, so one thing here, the horizontal emittance, and by the way, the phrase emittance, I don't know how much I've used it for you, it's a phase space concept. For us, it's a product of the size and the divergence. So for instance, the accelerator people would put that in terms of the RMS quantities, sigma, sigma prime. They would say that the emittance is equal to sigma, sigma prime. It's the product of the size of the beam and the divergence of the radiation. So roughly sigma and whatever the angle is, let's say the central radiation cone angle. So that's emittance. So is very big in the horizontal direction, okay, because D in the horizontal direction is so large, okay? In the vertical direction, it's not. But what the accelerator physicists tell us is that this horizontal emittance, and therefore how wide is the ellipse, scales as gamma squared over n cubed, where n in this case is how many bends. So remember, we had a regular polygon with 12 sides or 20 sides, and then there were the bend. At the end of every straight section, the electrons would get bent into the next straight section. But in order to keep this small, they all, until now, would take that bend from one straight section into the next. They'd take it not in one strong bend, but they'd take it as 3 little bends, okay? And so the ALS was called a triple bend achromat, meaning that the bending magnets between each successive straight section, the bend would be taken in 3 parts. So this would be n equals 3, and gamma is whatever gamma is. What the ALS is proposing to do is to go from a triple bend achromat to essentially 9 small bends. So they're going to increase n by 3 in order to get this to be not so spread out, okay? Not have the electrons being kicked so hard as they go through the magnetic field that when they throw out photons, there's a little momentum kick. That's what's producing this widespread. So reducing the angle, and again, so the ALS, for example, is planning to increase this by a factor of 3, and the emittance, the horizontal emittance, and therefore the width of this is going to decrease by 3 cubed. So in your homework, one of the homework problems, it says, okay, how much do we expect the coherent power to be increased at the ALS? Well, there's 3 factors that play a role here, but this is the first one. Because we're going from a triple bend achromat with 3 sub bends at each intersection, we're going to go to 9. We're expecting to get a factor of 27. Coherent power depends on how much flux there was radiated. And if you remember, our formula for power radiated had a gamma squared in it. Should I go backwards, maybe? Yeah, I probably have to go back too far. Yeah, the power radiated depends on gamma squared. Well, the ALS upgrade is going to go from an energy of 2 GeV to an energy of 1.9, I'm sorry, they're going from the present 1.9 GeV, where gamma is a little less than 4,000, they're going to go to 2 GeV. So from 1.9 to 2, the gamma will increase, and it's a squared. They're going to get another 5% out of that. So they just got a 27 because of the increase in number of bends, because they increased gamma, again, in beam energy terms, from 1.9 to 2, you square it, it's a 10%. So they've got a 2.7 and a 1.1 factor. And what else? Oh, also, maybe that's not so. Also, well, the brightness will, the brightness and the coherent power will change. You'll see that the coherent power depends on, you'll see it in a moment, is n squared, but you could see it here. This is a power, and it's in a solid angle. That's kind of what's shown here. So the solid angle would be pi theta squared is going to be 1 over n squared. They're going to, in addition to changing the emittance, they're going to introduce an undulator with shorter periods. Shorter periods. I think it's going to be something like maybe 2.6 centimeters, which is smaller than what they had before. And that is going to get them a larger number of oscillations. So the number of oscillations, capital N, again, is going to be squared, and it's going to go from something like 200 cycles. I forget what the number is. We'll get to it in a moment, but there's also going to be a factor there. Whoops.
So, Professor, can I ask a question?
Yeah, well, that would be wonderful. Thank you.
So just in this slide, so is this like you have mentioned, like the triple band in ALS, is that the same with the super band beamline, or they are different?
Yeah, they're different. So between the different straight sections, you have to bend the electrons in. And for the triple bend achromat, the bending magnet is broken up into 3 smaller parts so that they're not as disruptive, okay? And now they're going to go to a 9 bend achromat, even more gentle. The super bend is just the opposite. It replaces the 3 the three soft turns into one really strong bend. And the magnetic field will be much higher there. And as a result, it's going to give it much higher kicks, and it's going to get to higher photon energies, but it's not going to help the emittance. It's going to make the emittance larger, not smaller. Yeah.
Okay, thank you.
Yeah, that was a good question. Thank you. Okay, so this is just for references for people who want to read more about this. And Mikhail Eriksson and others had a whole issue of the Journal of Synchrotron Radiation a few years ago. And this is that same formula again, that the horizontal emittance depends on the energy squared of the electrons and the cube of the angle. This is the triple bend. This is the angle that the electrons would make. So this is going to be reduced by a big factor, and that's a cube. And this is the beam, this is the electron energy. So for the ALS, it's going to go to 2 GeV. But for instance, at argon, I think they're presently at 7 GeV. They're going to drop down to 6. But for instance, compared to the ALS at 2 and they're at 6, their beam energy is 3 times higher, the energy per electron, and it's squared. So for them to get the emittance down is a lot harder. It's 9 times harder for the hard X-ray facilities to reach a circle than the soft X-ray machines like the ALS or BESI. And as a result, ESRF and APS will not get to a little circular beam. They'll take their very big ellipse, highly eccentric ellipse, and they'll collapse it significantly, but they won't get to a circle. Okay. I don't want to spend time on this, but just as a friend, Richard Garrett in Australia, made a graph of how the emittances, he normalized it to gamma squared. So it's really just looking at the sigma values. And for instance, he's showing the 3rd generation facilities, that's here, all the present facilities. And here's the ALS, okay? And the ALS he's showing is going to drop down just about a factor of 100, okay? Okay, oh, this is, what's in the name? So we call these things diffraction limited storage rings. But in fact, a better name would be 4th generation storage rings, because when they say diffraction limited storage rings, what they mean to imply is that the radiation that comes out is has complete spatial coherence. And in fact, it's not quite true. The beam size will be just what you want, but the divergence of the electrons is not corrected. So you don't quite get to the condition, you know, our d dot theta full width at half max, d dot theta roughly equal to lambda over 2. You will not be satisfying that condition for full spatial coherence. So some people, and in particular Robert Heddle of APS, and also he's also at SLAC, they have suggested that actually it's not the best name. It's misleading. We're not really going to get to a diffraction limited storage ring, okay? Okay, but at any rate, it is the name, and I think it's the name that's sticking as far as I can tell. Okay, so spatially coherent radiation. We talked about this when we were looking at spatial coherence, and we had our undulator, and we did spatial filtering and monochromator or filtering to get spatially and temporally coherent radiation, and we paid a big price. And at the ALS, for instance, with an undulator, we go from a watt of power, spatially, we go a watt of power in the central radiation cone, and then we put a pinhole in front of it and a monochromator to narrow the bandwidth, and we wind up losing some pretty good factors. So this is what it will look like. The ellipse is even more eccentric than shown. Okay. Now, this is the concept we're talking about. And we had a condition for this, and we're going to use that to understand the filtering. Yeah, so this is here's a diagram of some beamline, okay? And here's curves, tuning curves for different K values. Again, this would be K equals 0 down here. This is for the fundamental. And around up here is K equals square root of 2 or something like that. And this is the 3rd harmonic using formulas that we're going to use in a moment, or that we saw before actually for the harmonic. But this has also got spatial coherence and spectral narrowing here. And so we've gone from an output from the undulator, what we call the central radiation cone, about 1 watt, and we're down to less than 1 milliwatt. So we've lost a factor of several thousand in doing all that filtering. And these upgrades of the facility are meant to gain as much of that back as possible. So I would say here, we went from 1 watt, we're losing a factor of 5,000, right? Microwatts to watts. So we're losing a factor, we lost a factor of 5,000 by doing all of these things. And we're hoping to gain back about a factor of 100 of that 5,000. So this is called the average power is called not central cone, but coherent. And it shows lambda over delta lambda, meaning it wasn't in 1 over n, but it was in something narrower. So the experimenter, the scientific group, needed not a 1 over n bandwidth, but they needed something narrower to probe the atoms of interest. Okay. Yeah. Okay, so this formula is really what I wanted to draw attention to. This is the coherent power. We start with power in the central radiation cone, or nominally 1 watt, and we do spectral filtering. We choose a narrow bandwidth, which is narrower than 1 over n. And if you look at this, suppose n was 100, and you chose delta lambda over lambda to be 1 over 1,000, like this, this is a loss of a factor of 10. So that's what this is. If you had made this one part in 5,000, then this would be 100, and this would be 1 over 5,000, so you'd lose even more. So you start with the central radiation cone, you do spectral filtering, and you do spatial filtering, and this is a term you need to pay attention to. This is following our formula that for spatial coherence, you'd need a product of d and theta, again here in terms of RMS, equal to lambda over 2 pi. And for the vertical direction, the same, you'd want d and theta product to be, again, lambda over 2 pi. That's what the square is for. One of these goes with this one goes with the horizontal, one goes with the vertical. So when you put a small pinhole in there to do this, you're going to lose some factor. And the factor depends on what is your wavelength and how big is your emittance or phase space, okay? So, so this is the price you're paying for spatial filtering, for putting the pinhole in. For the lambda you have and the collection angle you have, your D is too big. How big is it? You know, and so this factor, which is accounting for both vertical and horizontal, gives you some factor, okay? And there's a beamline efficiency. You put all these mirrors in there and they have, if you're lucky, an 80 or 90% reflectivity, but after a few months, they have a carbon deposit on them and that reflectivity gets decreased a little bit. You have a grating, which you're going to produce some spectrum, and you're not only going to pay a price by choosing a narrower spectrum, but also the grating itself is not 100% efficient. So the combination of the mirror losses and the grating losses, there's some beamline efficiency. In the soft X-ray region, like for the ALS or Bessie or those, we use a rough number of 10%. For the hard X-rays, this beamline efficiency is actually quite higher. The glancing incidence is about the same, but rather than have a grating monochromator, I got to get rid of something. You'll have a crystal monochromator, which will be, excuse me, I want to get rid of this. The crystal monochromator is much more efficient, around 10 kilovolts. So for the hard X-ray machines, it won't be 10%, it'll be like 90%. Anyway, it's this formula that I want you to catch. We've shown how to calculate the power in the central radiation cone, and even for how to do that for harmonics. Now we added this JJ squared term. If we want to calculate the coherent power, we need to put these other two factors in for spatial and spectral filtering. And that's what's coming soon. Yeah. Oh yeah. So we saw this before. Okay, here are some tuning curves for coherent power with a monochromator. And in this case, it's even lower. It's microwatts. It's down to 10 microwatts, not 400. Okay, so here are the formula. Okay, what about taking the formula that we had? I need to do this. We had power in the central radiation cone for some harmonic and some bandwidth. Okay, and that was formula in the previous thing. But now we're going to take that and we're multiplying it by the two spatial filtering factors shown separately here. And that's giving us the spatial coherence for whatever harmonic it was that we were talking about. And there are, rather than put simply d and theta, we need to account for the fact that there were that the sigma and sigma prime values had little factors associated with them. Okay, this we don't need to worry about too much. Okay, just forget this for the moment. So anyway, we're going to go from power in the central radiation cone for some harmonic to coherent power, spatially coherent. That's all we're doing so far. And for spectral, we'll either say it's in a 1-over N band or a 0.1% or something else. The standard of the community is to do it in 0.1%. So we'll probably do that even for third and fifth harmonic. Okay, so this is what's going to come. We're going to take the existing formula and we're going to multiply it by these two factors. Okay, so here's the power in the central radiation cone. It says from slide 46, but I think the number may have changed. And look to see if it changed by 3. And because I added 3, I duplicated 3 slides, so it may be now slide 49 or something like that. I'm not quite sure. And you need to know that for the homework because the homework directs you to these formulas. Okay, so here's power in the central radiation cone that we had these two formulas just a little while ago. We started with our formula and then we added the JJ squared factor and put that here. And now we're going to go from power in the central radiation cone to spatially coherent power. And so we're going to take that same formula as before and we're going to do a d dot theta and compared with a lambda over 2 pi. And I don't know why there's a 4 pi there. Maybe I made a mistake, I'm not sure. And this is the D. Oh, I see where that's coming from. Sigma, this is not a D, this is a half D. Okay, and these things are all getting squared. So basically, this is a correction which I don't think we should worry about here to the beam size. It's just saying that if you look back at the beam, and it seemed to be coming from a small spot. If you were looking on axis, you'd just see sigma, or twice sigma as the beam diameter. But if you were looking at it from at the edge of the central radiation cone, the source would seem a little bit larger. What used to be a circle would be somewhat elliptical just because of the angle you were looking at it. So there's a little correction. The facilities all take this into account very carefully. I think for us, it's not going to change our numbers much. We can leave it out. And the same thing here, we can use the central radiation cone. The divergence factor won't be such a big thing, okay? Okay, and we can convert watts into photons per second and change the units. So it says here, let's look at a special case, but a common case, where the correction for the beam size, because you're looking at it from an angle at the edge of this central radiation cone, let's just say that this term is not so important. And for the ALS, in fact, that'll be the case. And the same thing for the angles. The main thing we need to worry about is the central radiation cone. So when we go back to this slide, we would leave this term out. We'd say it's relatively small compared to the central radiation cone. We'd leave this out compared to the beam size seen looking straight onto it. And so the sigma squared is going to stay in the formula. Central radiation cone, remember that's 1 over gamma square root of n, or for a harmonic, it'll be 1 over gamma square root of nn, little n, big N. okay, like this, okay? This will be the central radiation cone angle. And so we'll forget this, and we'll forget this, and this one we're going to replace by this. So a lot of things will simplify, and this is what the formula will look like for the coherent power averaged over time in some harmonic, and this is written for a 0.1% bandwidth. Okay, so it's spatially coherent and somewhat narrow width, spectral width, and the formula, just following all the things we said before, is the factors that we started with and the JJ squared, but these other terms now appearing, and the beam size, all that will be left with is the sigma squared. Okay, so we still have the JJ squared to deal with here. I haven't made that approximation yet, but we're about to. And one thing to notice is that for coherent power, which we didn't see with power in the central radiation cone, but coherent power, things are adding in phase. And there's always this n squared effect when things add in phase. And we see that there's this product of n squared. So that coherent power depends on the number of periods squared. And this is where the ALS upgrade, let's say not so much the fundamental, n equals 1, but by using an undulator which has something like 150, I think it has 150 periods, n equals 150, versus the old one where it was 89, we get another factor here. So when I was saying there were 3 factors, there was the 3 cubed by the bending magnet going from triple bend to 9 bend. We're going to get 3 cubed was 27. Then because we changed gamma, we were going to get another 10%, because we went from 1.9 GeV to 2, and it goes as the square of gamma. In fact, the coherent power, as I see here, depends on the 4th power. So maybe it's a 20%. And then the number, because they use an undulator with more periods, they're going to get another factor of, what is that? Yeah, I think it was something like 150 divided by 89 squared. I'm getting a number that's too big, but it's in the homework problem, and that's the 3rd factor. So the third, in one of the homework problems, is it asks you, how much do we think the coherent fluxes or coherent power is going to increase? Well, it's the 27, the 10% or 20% here, and another factor here because the undulator that they're going to use has more periods, and it goes as the squared. Okay, what do I want to say here? Oh, okay, this is just introductory things that we've heard before. What this is at the bottom is beginning a set of slides to do what is the calculation for the ALS. Oh, and here we go. So here's the 2G, it's going to go from a 3-bend acromat to a 9-bend acrobat, and it's going to go from, I think, 260 or 270 microns horizontally to 10. So that's going to get us a 27 all by itself. The new value of the beam energy is now going to 2 GeV. So this is going to get some factor here. And the undulator that they're going to use and that they're basing their numbers on has 150 periods divided by 89. So in fact, that was a big number. 150 divided by 89 squared. It says they're going to get another factor of 2.8. So those are 3 factors that are going to contribute to why they say they're going to get something of order 100 increase in coherent power and in spectral brightness. So this was introducing really the homework problem. For the ALS parameters, this is what the formulas start to look like, and you can use these in that homework problem, okay? This is in practical units for power. This is in practical units for photon flux, make the approximations I told you about, which was to leave out this part and leave out this part, okay? And then these are slides. This is where I didn't want to bother you, but actually the homework problem involves some of this stuff. I think you can ignore this and just do the homework problem, but that's what's here. These were where we were really trying hard to make sure that we were getting the right answer and that it matched what everybody else was getting, and despite the different definitions of the central radiation cone. So what am I saying here? Yeah, this is too much about central radiation cones. Okay. Oh yeah. One of the things, somebody asked about this in class, and that was, what about gamma? What could increase the spectral width besides the Fourier analysis of the so many cycles, you know, the 1/n bandwidth, spectral bandwidth? What else could happen? And I said, well, actually, not all the electrons have the same value of gamma. There's a little spread to it. And that happens because some electrons radiated more power and they lost more energy, and so they're slower, and their value of gamma is a little lower. And we have that RF cavity to bring them back into shape again. But basically, there is some spread to it, and that will increase the spectral width of the radiation. And this slide is just a lot of detail about that. How much of an effect is it at the ALS, I think, is probably the example. Yeah, at the upgrade of the ALS. And it turns out it has a little effect. It has an effect. It's not negligible. And I told you that usually delta gamma over gamma, I told you incorrectly, was about 10 to the minus 4. Well, it is 10 to the minus 4 for the free electron lasers, but for the ALS and the synchrotrons, it's more like 10 to the minus 3. Okay, and so that means, and this gets squared, the gamma, the difference in gamma gets spread out a bit. So this sigma gamma means delta gamma over gamma. That's what it means in RMS terms. And it's about 10 to the minus 3. And this is just some details then if you want to read about that. But there is a question where it asks you, what else will cause a spread in the spectral width of undulator radiation? And it is that there's a little spread in the beam energy. Okay. And so these are curves then which we've been looking at for, it says for the present ALS lattice. So power in the central radiation cone is not going to change much, except that you might change the undulator parameters, so, and the beam energy. So there will be a little bit of change because of that. But the big change is going to be because of these sigma values. Oh yeah, so here are the sigma values for the ALS, 260 microns horizontally and 16 microns vertically. So they're going to change these both. They're hoping to reduce both of them to 10 microns. So there's a gain of 26 here and 1.6 here. Okay. So these are the old curves. The central radiation curves will change a little bit because of the undulator and the beam energy. What will really change is these curves. These will go up the factor of 100. Okay. And this is an ALS elliptically polarizing undulator. Somebody asked about that. There is one at the ALS. These are all numbers for the existing beam parameters. But I just thought I'd show that there is, in fact, an EPU at the ALS. And this is for spring 8. This is their old numbers, and you can see how highly elliptical their beam is also. We talked about these things before, about spatial coherence, so we don't need to do them again. Oh yeah, so we're running out of time. I decided that if you want to read about bending magnet radius, bending magnet performance, and the critical photon energy, you can look at these 3 slides, or you can read the section in the book on bending magnets. But I wouldn't call it hokey, but it's not as precise as everything else we've been doing. So what I'd like to tell you about instead is just take this single curve for bending magnet radiation, okay? That I told you about this before. This is an example of bending magnet photon flux versus photon energy. The example is the ALS, and what's important is this critical energy which separates where 50% of the radiated power is on this side and 50% of the radiated power is at the other side. And for the ALS, that critical photon energy, which we calculate in the book, is roughly 3 keV. And quite importantly, if you just drop down if you're willing to drop down just a factor of 10 in photon flux from this operating point to this operating point, you'll have increased the energy of the photons by a factor of 4. So by going from E crit to 4 E crit, which would be 12 kilovolts at the ALS, which is just terrific for hard X-ray protein crystallography and many other material science experiments, you've only lost a factor of 10 in power. It's not the end of the world. And it's on a bending magnet. So this is all I'm going to say about the bending magnet curve. It's a very broad spectrum because you don't see a lot of oscillations. You just see a glimmer of a small fraction of an oscillation, a curve. Okay. Does anyone want to say anything about this? Okay.
Sorry, Professor, I had a question.
Yeah.
You might have explained this earlier, but
It's okay.
so undulators and bending magnets are obviously like two different setups, but then how does the ALS have a bending magnet along with the undulator setup?
Yeah. So I don't want to switch back, but remember with the regular polygon I showed you with a lot of straight sections?
Mm-hmm.
So in each of the straight section, there'd be an undulator with perhaps a different period, depending on what kind of photon energies they were doing. Was it for chemistry, molecular science, or was it for magnetic materials or something? So in each of the straight sections, there would be a different undulator. But to go from one straight section into the next straight section, you have to bend the electrons to get into the next straight section, to change their direction and go into the next straight section. And that's a bending magnet, okay? And we could have one bending magnet of a very strong magnetic field, or we could break it, as the ALS does, they break it down into 3 bending magnets with this field, okay? That's the so-called triple achromat. So again, between the straight sections, you need a magnetic field to deflect the electrons. And that's where this critical photon, and so there's bending magnet radiation between every straight section, and we use it, okay? So good question, good timing for a question. If you had a wiggler, I told you, looks like an undulator, but it just has only a few periods. Rather than 100 cycles, it'll only have like 3 or 5 cycles. And then as a result, the magnetic fields can be quite a bit stronger and really jerk the electrons, much higher acceleration. The photon energy depends on acceleration, or the power depends on acceleration squared. But at any rate, you get to much higher photon energy. So the wigglers, they screw up the beam somewhat. They're not as popular anymore, but they get you to a radiation that looks like bending magnet radiation, but it'll be higher by how many half periods there are, because every half period jerks the electrons and they give off photons, always in almost the forward direction. But at any rate, so if you had a wiggler, what looked like an undulator, but if you had a periodic magnet with only, let's say, 3 cycles, that would be 6 half cycles. You'd get increased radiation by a factor of 6, but more importantly, you get out to higher photon energies. And in the early facilities, it was a way to get hard X-rays. Nowadays, less popular. We just have a few minutes, but I wanted to mention to you various ways to get a varied polarization. So here's one kind. This was due to Kwang-Jae Kim when he was in Berkeley, and he shows one undulator with its magnetic field pointed, let's say, in the vertical direction, and then followed by another undulator turned sideways, so the magnetic field, in this case, would be horizontal. So when the electrons come through the first one, they oscillate horizontally, and then they go into the next one. The magnetic field is horizontal. The electrons oscillate vertically. So shown here, in one section, they're oscillating in one plane, in the other, they're oscillating in the other. And by changing, and so you're producing a wave train with one polarization and a cross polarization. And by changing the time of transit of the electrons from the one to the other, remember these two wave trains are almost moving with the electrons, so they're almost overlapping. So here you have two close to overlapping wave trains. In fact, they are largely overlapping. They're just at the edges that they're not. By putting something in the middle here to just slow down the electrons a little bit, you can shift these two patterns to overlap. And you can get their electric fields to overlap to give you any polarization combination you want. You can have circular polarization going this, clockwise, counterclockwise. You can get them to add up, so they have a minus 45 degrees or a plus 45 degrees polarization. You can get whatever you want. There are other techniques that are actually more popular, and they're called apple undulators, where they have magnet structures that look like this, and you can slide one compared to the other. So it has the same effect, but they are called apple undulators. And these were in this one. This is the so-called Apple II, and they produce radiation, which is shown here to be circularly polarized. And by sliding it back and forth, you can get whatever polarization you want. And here is the crossed undulator and the Apple II undulator. Okay, that's how they seem to work. Okay. So this gives you some idea. This is a Japanese invention by Sasaki-san, and it's showing that by moving the different magnetic components, you can get whatever polarization you want, and they are used throughout the world. So we're about out of time. This is just some of the synchrotron facilities. I say this because I use it at different schools, and I ask people, okay, if you're working in Taiwan, what is gamma for your facility? Remember, it's 1957 times the energy in GeV. So for the Taiwan source, it'd be almost 2,000 times 1.4. So it's 3.8, something like that. Oh, yeah. So here are the beamline parameters. I told you this was in the book on page 150 something, 154. There was this table that just showed the ALS and the argon facility. But for instance, if you go down here, this is the present sigma values for the ALS and the sigma prime values, which are divergence, and some information about the wiggler that we have there, some undulators. The one that's chosen here is an undulator with 89 periods, 5 centimeters each, some of the parameters, what kind of spectral brightness you get. Okay, and so this is just for the consumption of people who'll see these slides and are more interested in other facilities. And so there's several combinations. So for instance, Monday and Tuesday of this week, I may have told you I lectured on synchrotron radiation in the European school called Hercules. And that facility is at ESRF. And a lot of the people were there from Max 4 and Bessie. And so I show these different tables depending on what school I'm teaching at. This we've talked about so much, we don't have to say it again. Oh, yes. So with just a few minutes left, we want to we have radiation coming out of our synchrotron, and we want to get it to our sample. We need a beamline. We need some sort of monochromator, and we need some optics to bring it there. And so this is an example of a beamline at the ALS with some optics that are going to collect the radiation and bring it to our sample, and a grating monochromator. This is a nicer picture of the same thing. And also there are deflection mirrors that you can put into the beam to deflect the beam left or right into different branch lines. So a beam line has several branch lines, and the way that's done is by injecting mirrors. So there'll be a position of a mirror in to deflect left, to deflect right, or no mirror, goes straight ahead. So you have 3 different branch lines. So the radiation will come to 3 different stations. And that's a really good thing because these things run 24/7 and people get really tired. And so if good idea is to take maybe 2 shifts, one to get everything set up, one to get data, but then pass the midnight shift to somebody else, okay? And here's what one looks like. This is at the ALS. If you know Tony Warwick, that's Tony. This is about the time structure, which we talked about, right? So we're getting, at the ALS, the pulses are coming every 2 nanoseconds, pulses of electrons, and the width nowadays is around 70 or 100 picosecond. I'm not quite sure what they're running right now. Oh yeah, this is interesting. What are the relative merits of the bending magnet, the wiggler, and the undulator? So the bending magnet gives a broad spectrum, a decent photon flux, very little heat load on your optics, so it's an inexpensive beamline to build, and it's easy access. Graduate students generally could find easy access to beam time there. The wiggler radiation looks like a bending magnet radiation, but it's a higher photon energy, typically by factor of 3, and you can also go to 4 crit. It has more photon flux. It has an expensive magnet structure, so it costs more, and it puts out so much power that the first optics it hits would melt without water cooling and less access. And then the undulator has the brightest radiation, some degree of coherence, and it's expensive, and access is competitive. And these are just some references, okay? For people who are interested in diffraction, maybe scattering too, you might want to look at this book by Als Nielsen and McMurrow. It's a very popular book, and it doesn't explain some things, I think, as well as we have, but if you're interested in diffraction and perhaps scattering, this would be a book to have a look at, okay? And I think that's where we're going to end it. Yeah, these are the same references, except that has some additional ones, like the one from Carol McDonald. Is a relatively new book. It has a lot of numerical examples worked out, okay? And then there are the FEL books. And if someone's interested in accelerated physics and how it plays into all of this, there is a summer school every year for accelerated physics. And on several occasions, and people write up really extensive notes, and you can get college, university credit for taking that summer class. But there's a book out that Alex Chow wrote with others called Handbook of Accelerated Physics and Engineering. And if anyone was interested in working with synchrotron radiation, it's a paperback, and it has really great explanations of things. And we're back. So we're back, and we're just running out of time. So I'm sure that was breathtaking. I'm sorry for that. Now you have the homework assignments Stefan will announce. And oh yeah, and he said that you could find the solutions at the B course site by looking where he has the homework folders, and you'll find the solutions there for the previous examples. So you could take a look at that if you want, okay? How are we doing? Was there any? Okay, thank you both. Andy, you didn't respond. And Xiao Zhou.
Oh, to what?
How are we doing? Did we accept most of what was there?
Oh, yeah. For the presentation, right?
Yeah, for just
So yeah, I mean, one of the things that I was curious about was the setup, and when it comes to these reflectors, like how big are they, and I guess how, I know the visualization of where you would like the beam to go is one thing, but actually having it hit a precise location is another. How do they go about, you know, setup, I guess, in some of
Yeah.
these places.
Well, so for the mirror, how big is the mirror? Was one of the things you asked, right?
Mm.
So we know the beam size is quite small, right? The vertical beam size is, microns, 10 microns or 20 microns. And of course, it has some divergence, the central radiation cone. So it gets bigger as it goes out, but still, it doesn't get very big. So the beam size vertically would probably be 1 millimeter. Horizontally, it's a lot bigger. And you have glancing incidence optics that spread the beam out a great deal. So even if you had in the vertical direction, it's not the bending, the mirror direction, but you take that beam size and you spread it out. So you wind up needing a mirror, which is a 1/2 meter long. It's not very high, maybe 1 centimeter by 1/2 meter. So these are really long mirrors. They need to be made by the best of the best to get a shape that you want, which is sometimes flat, but even polishing a 1/2 meter is that's a challenge. And if you put curvature into it, that's where I told you about this JTech company comes in. If you want curved mirrors to refocus on your sample, you need a really high quality mirror. The alignment is not so difficult because the synchrotron radiation is just coming out. So you can put your mirror in place, and it's almost like having a helium neon laser to align your optics and get them on.
Oh, okay.
Yeah. That turns out to be quite simple. Yeah. The
Okay,
big
but
problem
those
is
are the tricky.
the big problem is paying for that long, highly polished mirror, because a little roughness at glancing incidence would just splatter radiation all over. So it's really that is a challenge, has been a challenge over the years.
Okay. Well, thank you.
You're welcome. So this brings us to the end of synchrotron radiation. And so next class will start on, next meeting will be on the evolution then, using this knowledge of undulator radiation, how do we get to an FEL? So again, we're going to make the undulator really long. We're going to go from a few meters to 1/2 kilometer. We're going to make the electron beam much smaller so it starts coherent, okay? And we're going to increase the current, which mainly means that we're going to have a lot more electrons in the bunch and they're going to be radiated. And we're going to see that this leads to increases in power by many orders of magnitude. Yeah. So we have our last homework problem. There's only 3 problems. The first 2 are quite simple, and I helped you a lot, I think, with the comments here today. And the third one has to do with those formulas, but applied to the ALS upgrade. And if it gets confusing there, because I said, you'll know what slide to use. If we're asking for a harmonic, you need to use a formula that had the N in it, the harmonics. And if it's asking for just central cone power, that's one thing. If it's asking for coherent power, so you'll have to go to the slide that has the formulas that are relevant to you, okay? So they were numbered, but again, the numbers may be off still by a factor of 3, not a factor. They may be off by 3 because I repeated 3 slides. But if anyone has any issues with the homeworks, you can contact me directly, or Leona, or Difan. Don't hesitate. If you get hung up on something, send us an email or something. Okay? Okay, have a good evening.